This is Lecture 8, Correlation. By the end of this lecture, you should be able to know when it is useful to conduct a scatterplot and Pearson's correlation coefficient analysis, construct and interpret a scatterplot, understand the intuition behind a Pearson's correlation coefficient, calculate and interpret a Pearson's correlation coefficient, understand the limitations of using a Pearson's correlation coefficient. In this lecture, I will discuss how to conduct and interpret scatterplots and correlation analyses. If you have interval and ratio level independent and dependent variables, you could use a scatterplot to interpret the relationship between the variables. A scatterplot is just a graph that plots the independent variable against the dependent variable. It allows us to determine if the independent variable has an effect on the dependent variable, and if so, if that effect is positive or negative. In order to construct a scatterplot, place the independent variable on the x-axis, place the dependent variable on the y-axis, place the appropriate numerical values on the axis, and then plot the data on the graph. In order to demonstrate how to construct a scatterplot, I will use the following example. The dependent variable is net migration, a variable that measures how many people enter and leave a country in a year. Positive values indicate more people enter than leave, and negative values indicate more people leave than enter. It is a ratio level variable. The independent variable is GDP per capita. It is ratio level as well. The hypothesis is, as the GDP per capita of a country increases, net migration in that country increases. This is a scatter plot of the data. Net migration, the dependent variable, is on the y-axis, and GDP per capita, the independent variable, is on the x-axis. The appropriate values are on each axis, and the dots represent the values for each individual observation for both variables. To interpret the scatter plot, you should draw a line through the middle of all of the dots. The slope of the line will tell you if there is a positive, negative, or no relationship between the variables. Here is a scatter plot that demonstrates a positive relationship between the independent and dependent variables. I drew a line through the middle of all of these dots. The slope of the line is positive, indicating that as the independent variable increases, the dependent variable increases as well. Here is a scatter plot that demonstrates a negative relationship between the independent and dependent variables. I drew a line through the middle of all these dots. The slope of the line is negative, indicating that as the independent variable increases, the dependent variable decreases. Here is a scatter plot that demonstrates a neutral or no relationship between the independent and dependent variables. I drew a line through the middle of all of these dots. The slope of the line is very close to zero, indicating that as the independent variable increases, the dependent variable does not change. Going back to our example, I drew a line through the middle of the points on the scatter plot. The slope of the line is slightly positive. Based on the scatter plot, it does appear that as GDP per capita increases, net migration increases. But is the effect of the independent variable on the dependent variable large and consistent enough to indicate that the independent variable really does have an impact on the dependent variable? We need to determine if the relationships we observe are large and consistent enough to confidently conclude that the independent variable has an impact on the dependent variable. We can use a correlation analysis to do this.
A correlation analysis is useful when we have a 3 or more category ordinal level independent variable and an interval or ratio level dependent variable, or interval or ratio level independent and dependent variables. A correlation coefficient tells us the direction of the relationship between two variables. It tells us as if one variable increases, the other variable increases, decreases, or stays the same. A correlation coefficient ranges from -1 to 1. Correlation coefficients close to -1 indicate a strong negative relationship between two variables. In other words, as one variable increases, the other variable tends to almost always decrease. Correlation coefficients close to 1 indicate a strong positive relationship between two variables. In other words, as one variable increases, the other variable tends to almost always increase as well. Correlation coefficients close to 0 indicate as one variable increases, the other variable does not change. This is how you calculate a correlation coefficient. The numerator is the sum of the product of each individual observation x minus the mean of x, and that value divided by the standard deviation of x, and each individual observation y minus the mean of y, and that value divided by the standard deviation of y. The denominator is the number of observations minus 1. What the correlation coefficient measures is whether each individual x observation deviates from its mean in a similar pattern to its corresponding y deviation from its mean. I created a series of graphs to demonstrate what this means substantively. Imagine you have a graph with 4 quadrants. In quadrant A, all observations are below the mean of x and above the mean of y. In quadrant B, all observations are above the mean of x and y. In quadrant C, all observations are below the mean of x and y. And in quadrant D, all observations are above the mean of x and below the mean of y. When there is a positive relationship between x and y, when an observation is below the mean of x, it is below the mean of y. In addition, when an observation is above the mean of x, it's above the mean of y. All observations vary from the means of x and y in a similar pattern. When there is a negative relationship between x and y, when an observation is below the mean of x, it is above the mean of y. In addition, when an observation is above the mean of x, it is below the mean of y. All observations vary from the means of x and y in a different pattern. When there is no relationship between x and y, there is no pattern to how observations vary from their means. Observations are located in each quadrant. As a numerical example, consider the two following variables, variable x and y. The mean of variable x is 50 and the mean of variable y is 10. In observation y, x is 70 above the mean of x and y is 20 above the mean of y. For observation 2, x is 30 below the mean of x and y is 5 below the mean of y. This implies that there is a positive relationship between x and y. When an observation is above the mean of x, it is above the mean of y. When an observation is below the mean of x, it is below the mean of y. Next, consider the following two variables, variable x and y. The mean of variable x is 50 and the mean of variable y is 10. In observation 1, x is 70 above the mean of x and y is 5 below the mean of y. For observation 2, x is 30 below the mean of x and y is 20 above the mean of y. This implies that there is a negative relationship between x and y. When an observation is above the mean of x, it is below the mean of y. When an observation is below the mean of x, it is above the mean of y. Next, consider the following variables, variable x and variable y. The mean of variable x is 50 and the mean of variable y is 10. In observation 1, x is 70 above the mean of x and y is 20 above the mean of y. For observation 2, x is 30 below the mean of x and y is 20 above the mean of y. This implies that there is no relationship between x and y. There is no consistent pattern in how each individual observation deviates from the means of x and y. The correlation coefficient also takes into account the extent to which individual observations deviate from the means versus how often observations deviate from the mean overall. You can calculate a large deviation from a mean for an individual observation, but if most observations strongly deviate from the mean for that variable, then the large deviation for that individual observation is not significant. Now I'm going to show you how to calculate a correlation coefficient. I will use data from the beginning of the lecture that measures the GDP per capita and net migration of individual countries. Note that I'm only going to show you 4 observations in the slides, but I used a total of 178 observations in this analysis. The first thing you do is calculate the mean of x and the mean of y. Just as a reminder, as with the rest of the calculations, I did this for all 178 calculations, or 178 observations. Next, you calculate the standard deviation of x and y. You learned how to do this in Lecture 6. Next, you subtract the mean of x from each x. 340.93 minus 9,902.18 equals negative 9561.25. You do this for the rest of the observations. Then you divide the values from step 3 by the standard deviation of x. Negative 9561.25 divided by 14484.48 is negative 0.66. You do this for the rest of the observations. Then you subtract the mean of y from each y. Negative 381,030 minus 5832.34 is negative 386,862. You do this for the rest of the observations. Then you divide the values from step 5 by the standard deviation of y. Negative 386,862 divided by 706,365.1 equals negative 0.55. You do this for the rest of the observations. Then you multiply the values from steps 4 and 6 together. Negative 0.66 times negative 0.55 is 0.36. You do this for the rest of the observations. Then you add all the values from step 7 together. When I did that, I got 69.12. Remember that I used 178 observations, but I'm only showing you 4 here, so the sum here should be different than the sum of these 4 observations. Then you divide the value from step 8 by the number of observations minus 1, or 178 minus 1, which is 177. 69.12 divided by 177 is 0.39. This gives you your correlation coefficient of 0.39. Remember that the correlation coefficient ranges from negative 1 to 1. And it tells us if there's a positive, negative, or neutral relationship between two variables. Unfortunately, there's no consistent way to interpret the results of a correlation analysis. The interpretation can sometimes be subjective. Here is a general way to interpret the results of a correlation analysis that I want you to use in this class. If the correlation coefficient is between negative 1 and negative 0.75, then you should say there's a strong negative relationship between the variables. This means that as one variable increases, the other variable almost always decreases. If the correlation coefficient is between negative 0.74 and negative 0.21, then you should say there is a negative relationship between the variables. This means that as one variable increases, the other variable often decreases. If the correlation coefficient is between negative 0.2 and negative 0.1, then you should say there is a weak negative relationship between the two variables. This means that as one variable increases, the other variable sometimes decreases. If the correlation coefficient is between negative 0.09 and positive 0.09, then you should say there is a neutral relationship between the two variables. This means as one variable increases, the other variable sometimes increases and sometimes decreases with no recognizable pattern. If the correlation coefficient is between 0.1 and 0.2, then you should say that there is a weak positive relationship between the two variables. This means that as one variable increases, the other variable sometimes increases. If the correlation coefficient is between 0.21 and 0.74, then you should say there's a positive relationship between the two variables. This means as one variable increases, the other variable often increases. If the correlation coefficient is between 0.75 and 1, then you should say that there's a strong positive relationship between the two variables. This means as one variable increases, the other variable almost always increases. Using these criteria to interpret our correlation coefficient was 0.39. That would suggest that there's a positive relationship between the GDP per capita and net migration of a country. As GDP per capita of a country increases, net migration often increases. Generally speaking, when an individual observation's GDP per capita is above its mean, net migration is above the mean. And when GDP per capita is below the mean, net migration is below the mean. However, the fact that this is only a positive relationship and not strongly positive means that some observations don't follow this pattern, like the observations in quadrant A. There is also a significance test for correlation that helps us determine if variables are statistically correlated. I'm going to show you how to conduct the test in SPSS instead of by hand. Step 1 is writing the null and alternative hypotheses. The null hypothesis is the correlation coefficient is equal to 0. The alternative hypothesis is either the correlation coefficient is greater than 0 if you expect a positive relationship between your two variables, or the correlation coefficient is less than 0 if you expect a negative relationship between your two variables. Remember that a positive relationship implies that as the independent variable increases, the dependent variable increases, and a negative relationship implies as the independent variable increases, the dependent variable decreases. In order to demonstrate how to conduct a correlation significance test in SPSS, I will use the following hypothesis. As a country's political institutions become more democratic, GDP per capita increases. The null hypothesis for this example would be that the correlation coefficient is equal to 0. The alternative hypothesis should be the correlation coefficient between type of institutions and GDP per capita should be greater than 0 because I expect a positive relationship. Step is writing the decision rule. If the correlation coefficient is in the correct direction, as in positive when it was expected to be positive, or negative when it was expected to be negative, and the significance value is less than 0.1, then I can reject the null hypothesis. I can conclude that the independent variable influences the dependent variable in the way I expect. If the correlation coefficient is not in the correct direction, as in negative when it was expected to be positive, or positive when it was expected to be negative, or the significance value is greater than 0.1, then I cannot reject the null hypothesis. I cannot conclude that the independent variable influences the dependent variable in the way I expect. Applying this to our example, we have, if the correlation coefficient is positive and the significance value is less than 0.1, then I can reject the null hypothesis. I can conclude that as a country's political institutions become more democratic, GDP per capita increases. If the correlation coefficient is negative or the significance value is greater than 0.1, then I can reject the null hypothesis. Then I cannot reject the null hypothesis. I cannot conclude that as a country's political institutions become more democratic, GDP per capita increases. Step is running the test in SPSS. To run the test in SPSS, you click Analyze, Correlate by Variate. You place all the variables in the Variables box. Then you click OK. So here's SPSS. Click Analyze, Correlate by Variate. I place the two variables in my analysis, reg type and GDP per cap 08. in the variables box, then I click OK, and here's my output. The next step is to interpret the results. In this table, the cell that intersects each variable tells you the Pearson correlation coefficient between each variable. So going back to our example, the correlation between reg type and GDP per capita was 0.459. The next step is evaluating the decision rule. You start with the correlation value. If it is in the wrong direction, as you expected it to be positive, but it was negative, or you expected a negative relationship, but it was positive, you are done with the test. You cannot reject the null hypothesis. You have no support for your argument. If it is in the correct direction, move on to the next slide. Next, I will discuss the sig two-tailed test, which will tell us if the correlation coefficient is statistically different from 0. This test is similar to a significance test for a difference of means test, which we discussed in the previous lecture. It finds an appropriate value from the t-table, and then it calculates a t-statistic, which equals the correlation coefficient times the square root of the number of observations minus 2, and that value divided by the square root of 1 minus correlation coefficient squared. If this t-value is greater than the t-value from the t-table for a positive relationship, or less than the negative t-value from the t-table for a negative relationship, the null hypothesis is rejected. If not, then the null hypothesis is not rejected. Going back to the output, the sig two-tailed value in each of the cells tells you the results of the significance test for the correlation between the two variables that intersect that cell. If the sig two-tailed value is greater than 0.10, you are done with the test. You cannot reject the null hypothesis. You have no support for your argument. If the sig two-tailed is less than 0.10, you can reject the null hypothesis and conclude that the correlation is greater than 0 for a positive sign or less than 0 for a negative sign. Applying this to our example, we expected a positive correlation. We have a positive correlation. The sig value is 0.000, so it is less than 0.10. We can reject the null hypothesis and conclude the correlation is greater than 0. The last step is making a conclusion. If you cannot reject the null hypothesis, you have no support for your argument. You cannot make any conclusions about the relationship between the independent and dependent variable. If you can reject the null hypothesis, you can conclude that as the independent variable increases, the dependent variable either increases positive correlation or decreases negative correlation. You can also conclude how strong the relationship is based loosely on these criteria that I discussed earlier in the lecture. Applying this to our example, we have, as a country becomes more democratic, GDP per capita increases. Since the correlation was 0.459, I can conclude that there is a positive relationship between regime type and GDP per capita. This means that as a country becomes more democratic, GDP per capita often increases. Next, I would like to discuss two problems with correlation coefficients. First, all of these relationships between x and y here have different patterns, but they all have the same correlation coefficient. So a correlation coefficient can give you a general idea of the relationship between two variables, but it cannot tell you exactly what that relationship looks like. Second, correlation coefficients cannot tell you the specific relationship between an x and a y variable. They cannot tell you as the x changes by 1, by how much does the y change. That is what a regression analysis tells you, which is the subject of the final lecture of this course.
Throughout this course, we discussed different methods to analyze the relationship between two variables. Here is a metacognition card that summarizes when we should use these different types of methods to analyze the relationship between two variables. If you have nominal or ordinal level independent and dependent variables, you could either use a cross-tabulation analysis or a chi-square test. If you have an interval or ratio level dependent variable and a two-category nominal or ordinal level independent variable, you could use a mean comparison table or a difference of means test. If you have an interval or ratio level dependent variable and a nominal level independent variable with more than two categories, you can use a mean comparison table. If you have an interval or ratio level dependent variable and an ordinal level variable with more than two categories, you could use a mean comparison table or a correlation analysis. If you have interval or ratio level independent and dependent variables, you could use a scatter plot or a correlation analysis.